So this is an advanced higher chemistry video based on Unit 3, Research in Chemistry, and the topic for discussion is gravimetric analysis. So what is gravimetric analysis? Well, gravimetric analysis means any sort of analysis where we use the weight or the mass changes of chemicals to determine aspects of their composition. And the key bits of equipment that we would use a mass balance, we would use things like weighing books, and we would use desiccators to keep things dry and ovens to dry them. In terms of terminology, there are going to be four terms that you need to be able to define, describe, and use. So tearing a balance, weighing something accurately, approximately, weighing by difference, and the concept of constant mass. So tearing means resetting the value on a digital balance or even a manual balance to 0. On most balances, there is a button that's either called the 0 button or the tear button that you press, and it automatically does this. Before you weigh anything, you need to make sure that the balance is teared. And if you ever are using a balance and it's unable to tear, it means that the balance itself is not level and will not measure accurately, and so you shouldn't use it, and you should seek out your teacher or your technician to get that fixed. The second term is weigh accurately, approximately. Now the thing with this is that it seems quite contradictory. How can something be accurate yet approximate? But each word in this phrase applies to a different aspect of weighing. The accurately means that you're going to use a balance that can measure to 2 or 3 decimal places. It's no longer good enough an advanced higher to just weigh out a gram and just say that, oh, I weighed out 1 gram. You need to be able to say that you accurately weighed out 1.021 grams. That's what makes it accurate. Approximately refers to what you were told to weigh out. So if you were told to weigh out 1 gram, as long as you've weighed out approximately 1 gram, you'll be okay. So for example, if you were told to weigh accurately approximately 1.5 grams, some values you could do. So 1.487 grams to 3 decimal places is accurate, and it's also approximately 1.5. If you rounded that, it would round up to 1.5. Another mass, 1.52, is also accurate because it's been measured to 2 decimal places. It's not as accurate as the previous one, but it's also approximately 1.5 grams by rounding this time. If you rounded it, it would round down to 1.5. So that's what that means, and you do need to be able to explain what that means. That has been asked. Weighing by difference. So whenever you're weighing a chemical, you first need to weigh the mass of the container you're measuring it into, then weigh the total of what you've weighed and the container together, and the mass of chemical is your total mass minus your container mass. That's what you do for weighing by difference. Now, why does this matter? Why would you do that? Well, it means that you can keep your chemical in the same container while you leave it to dry or you leave it to absorb, and you can measure changes without having to transfer it into a different container each time. Because every time you transfer a chemical from one container to another, you lose some chemical. Some will stick to the spatula, some will stay in the original container. So if you can just use one container and weigh by difference, you're saving yourself a lot of time, and you're making sure that you're not losing any of your product. Constant mass. So if you've done a precipitation reaction from solution, or you're wanting to remove water from a compound, you need to make sure it gets completely dry. So what you can tell if this has happened is it will mean that no more water or no more solvent can be removed from it, which means essentially it will stay at a constant mass. So the only way you can prove that a material or a chemical is completely dry is by leaving the sample in an oven and weighing it like every 30 minutes or every day until the mass no longer changes. When the mass doesn't change, it no longer drops, and it's at constant mass, you can say that it is definitely dry. Now, when it comes to gravimetric analysis, there are two common types. We have a precipitation gravimetric analysis, and we have a volatilization gravimetric analysis. One involves producing a solid, that's precipitation, and the other involves getting rid of a liquid by getting that liquid to evaporate or dry away. So that's volatilization. We'll look at precipitation first, then volatilization, and then we'll look at two worked examples of how we use the technique. So precipitation is typically used to measure the mass of an ion in a compound. You start off with a soluble salt, which you weigh out so you know the starting mass of. You then add, you make it a solution, and you will add a chemical that will form a precipitate with the ion you want to measure. You then filter out that precipitate, and you always need to check the liquid, the filtrate that's gone through. You need to add more of that chemical that caused precipitation to the filtrate to check that no more precipitate can form. And you keep doing that and filtering until your filtrate stays clear when you add the chemical that causes precipitation. So you keep doing this filtration, test the filtrate, refilter, and repeat and repeat and repeat. When that happens, you will dry the precipitate to constant mass, and then you can use the percentage composition of your given element in the precipitate and the mass of the precipitate to determine the mass of the ion that's in the precipitate. And because you've made sure that all of that ion has precipitated, the mass of that ion in the precipitate will equal the mass of the ion in the starting compound. Volatilization is slightly different. Some compounds crystallize or solidify with trapped water or solvent in them. And they get written as a formula, then a centered dot, and then a number, H2O. And often it's X because that number can change. And we call that water the water of crystallization. Now, if we want to work out what X is, we weigh our chemical out in a weighing boat or in a container. We then put it in an oven and dry it to constant mass, and that helps remove any water. We can then measure mass lost from our sample. The mass lost is the water, and the mass remaining is your compound. And what you can then do is use a mole ratio to determine X. So from the mass lost, the mass of water, we can work out the number of moles of water. From the mass remaining, we can work out the mass of the chemical without any water. So in the example of copper sulfate, it would just be the CuSO4 is what remains. We can work out the number of moles of that, and then look at the ratio, how many moles of water to how many moles of your other part of the compound. So I'm going to talk through two different methods of determining the water content in hydrated barium chloride. Hydrated just means it has that point XH2O at the end. I'm going to go through the easier method first, which is volatilization, and then I'm going to show you how a similar thing can be done using precipitation. So the first method is the easy method using volatilization. We're going to weigh a sample, dry it to constant mass, work out the mass of water lost and the mass of barium chloride remaining, and calculate a mole ratio. So we've weighed our weighing boat and it's 2.348 grams. I've color coordinated all of our masses so we won't get lost. The mass of the weighing boat plus our hydrated barium chloride is 5.694 grams, And our mass of a weighing boat, barium chloride, after we've dried it, is 4.432 grams. So that's all the weighings that we've done. We can now work out some things. Well, the mass of hydrated barium chloride that we started with is going to be our 5.694 minus our 2.348 grams. We can also work out our mass of water. That's going to be the mass before drying, subtract the mass after drying, and that tells us our mass of water, which is 1.262 grams. Our mass of barium chloride we could actually work out in two ways. We could do what I've done here, which is take our mass of hydrated barium chloride and subtract our mass of water, or we could take our weighing boat and compound after drying and take away the mass of the weighing boat. Both of those calculations, if you do them, work out at 2.084 grams for this example. Now we've got our numbers, we've got our mass of water, we've got our mass of barium chloride, we can use a mole ratio. So we've got a mass, we've got a formula, we can use N equals M divided by GFM. And when we work it out for each one of these, we find out that the number of moles of barium chloride is 0.01 and the number of moles of water is 0.07. We then look at the ratio. Now, whenever we're doing this example, it's obvious that the water is 7 times the barium chloride, but often the numbers are not very obvious and they don't give you a full, nice, round, whole number. So what you do, always divide the moles of water by the moles of the other thing and then round it to the nearest whole number. In this case, it's 7, so that means we can fill out our formula as being BaCl2 0.7H2O. Or if we'd been asked to solve for x is equal to 7. Now, the harder method is precipitation, and this will have been an experiment that you will hopefully have tried. So by precipitation, what we do with our barium chloride is we dissolve it and we make a precipitate of the chloride ions. That allows us to work out the mass of chloride. From the mass of chloride, we can work out the mass of barium chloride, and then we can take that away from the mass we started with to give us our mass of water, and then use the ratio. It seems very, very, very long-winded. But because this methodology involves lots of different steps, it is highly likely that something like this can come up in paper 2 of your test. So understanding this and all the steps and things that you need to do will make sure that you're really prepared for any sort of gravimetric analysis question. So first step of this is making your precipitate. Anytime we want to precipitate chloride ions, we're going to use something containing silver that dissolves. So silver nitrate. So we've weighed out our hydrated barium chloride, 4.715 grams. That's really important that we keep that mass. Now we dissolve it in water, and in this case we need to add some acid. That's just to keep the silver nitrate in solution, so we need some nitric acid. Normally you just need to dissolve it in water. We add an excess of silver nitrate. Now the precipitation reaction is that silver ions react with chloride ions to form silver chloride, a solid. Now we use Buchner filtration, so filtrating under vacuum to collect the solid. We keep testing the filtrate with more silver nitrate until no more precipitate forms, and we keep filtering it and filtering it, filtering, testing, until we've collected all the possible precipitate. And we rinse it with a little bit of water and then a little bit of dilute acid to remove any impurities, so we know all we've got is silver chloride. We then dry it to a constant mass. Now this should be done in an oven and then leave it in a desiccator. Desiccators are there to prevent things from gaining mass. Keep things dry. The oven is what dries it. We had our weighing boat. We completely dried it with our sample inside, and we had 7.153 grams. The dry silver chloride is our dried sample and weighing boat minus the mass of the weighing boat, which comes out at 4.581 grams. Now we're doing our calculations. How do we calculate our mass of chlorine? Well, our gram formula mass of silver chloride is 143.4. The percentage composition of chlorine in silver chloride is 24.8. Now, if we had a sample mass of 4.581 grams, we know that 24.8% of that is chlorine. So we just multiply our 4.581 by 24.8%, and that gives us 1.136 grams of chlorine in silver chloride. All the chlorine in silver chloride started off as part of our barium chloride. So that's what we can now do. If that was the mass of chloride in barium chloride, we can work out the total mass of barium chloride. So the gram formula mass of barium chloride is 208.3. Our percentage composition of chlorine this time is 34.09. Now, slightly differently from last time, what we know is that the 1.13 grams of chlorine we have is equal to 34.09% of barium chloride. Using this, we could work out what the total mass, what 100% of barium chloride would have as a mass. So if 1.136 grams is equal to 34.9%, 100% is going to be 1.136 divided by 34.09 multiplied by 100, which gives us 3.332 grams. Now, way back at the start of this one, I told you that the total mass of sample we had was 4.715 grams. So we can work out the mass of water by taking away our mass of barium chloride from our total mass, 4.715 minus our 3.32, which is 1.383 grams. So now we're in the same position we were in with the volatilization, where we know our mass of barium chloride, we know our mass of water, we can work out a mole ratio using N equals M divided by GFM. Now this time, when we do it, we find out our barium chloride is 0.016 moles, our water is 0.079 moles. Now, if you did this, you might have rounded at different positions, so just be wary whenever you read through examples that different levels of rounding is accepted. Now what we do is we look at this. Look at the ratio and we divide by the smallest number. So in this case, we're going to divide each one by 0.016. When we do that, obviously 0.016 divided by itself is 1. With our water, we get 4.93. We round that to the nearest whole number, which gives us BaCl2.5H2O. Just showing you that the amount of water can vary between samples. Now that has been a go over of the terminology of gravimetric analysis, an understanding of what is meant by gravimetric analysis, and 2 worked examples of how to use volatilization and how to use precipitation to use and solve problems based on gravimetric analysis.